Chapter 3 of Science and Hypothesis. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Leon Meyer. Science and Hypothesis by Henri PoincarÄ. Chapter 3. Non-Euclidean Geometries. Every conclusion presumes premises. These premises are either self-evident and need no demonstration, or can be established only if based on other propositions. And, as we cannot go back in this way to infinity, every deductive science, and geometry in particular, must rest upon a certain number of indemonstrable axioms. All treatises of geometry begin therefore with the enunciation of these axioms. But there is a distinction to be drawn between them. Some of these, for example, things which are equal to the same thing are equal to one another, are not propositions in geometry, but propositions in analysis. I look upon them as analytical a priori intuitions, and they concern me no further. But I must insist on other axioms which are special to geometry. Of these, most treatises explicitly enunciate three. 1. Only one line can pass through 2 points. 2. A straight line is the shortest distance between 2 points. 3. Through one point, only one parallel can be drawn to a given straight line. Although we generally dispense with proving the second of these axioms, it would be possible to deduce it from the other two, and from those much more numerous axioms which are implicitly admitted without enunciation, as I shall explain further on. For a long time, a proof of the third axiom, known as Euclid's postulate, was sought in vain. It is impossible to imagine the efforts that have been spent in pursuit of this chimera. Finally, at the beginning of the 19th century, and almost simultaneously, two scientists, a Russian and a Bulgarian, Lobachevsky and Bolyai, showed irrefutably that this proof is impossible. They have nearly rid us of inventors of geometries without a postulate, and ever since the Académie des Sciences receives only about 1 or 2 new demonstrations a year. But the question was not exhausted, and it was not long before a great step was taken by the celebrated memoir of Riemann, entitled Über die Hypothesen, welche der Geometrie zum Grunde liegen. This little work has inspired most of the recent treatises to which I shall later on refer, and among which I may mention those of Beltrami and Helmholtz. The Geometry of Lobachevsky. If it were possible to deduce Euclid's postulate from the several axioms, it is evident that by rejecting the postulate and retaining the other axioms, we should be led to contradictory consequences. It would be, therefore, impossible to found on those premises a coherent geometry. Now, this is precisely what Lobachevsky has done. He assumes at the outset that several parallels may be drawn through a point to a given straight line, and he retains all the other axioms of Euclid. From these hypotheses he deduces a series of theorems between which it is impossible to find any contradiction, and he constructs a geometry as impeccable in its logic as Euclidean geometry. The theorems are very different, however, from those to which we are accustomed, and at first will be found a little disconcerting. For instance, the sum of the angles of a triangle is always less than 2 right angles, and the difference between that sum and 2 right angles is proportional to the area of the triangle. It is impossible to construct a figure similar to a given figure, but of different dimensions. If the circumference of a circle be divided into its equal parts, and tangents be drawn at the points of intersection, then its tangents will form a polygon if the radius of the circle is small enough, but if the radius is large enough, they will never meet. We need not multiply these examples. Lobachevsky's propositions have no relation to those of Euclid, but they are nonetheless logically interconnected. Riemann's geometry. Let us imagine to ourselves a world only peopled with beings of no thickness, and suppose that these infinitely flat animals are all in one and the same plane, from which they cannot emerge. Let us further admit that this world is sufficiently distant from other worlds to be withdrawn from their influence. And while we are making these hypotheses, it will not cost us much to endow these beings with reasoning power, and to believe them capable of making a geometry. In that case, they will certainly attribute to space only 2 dimensions. But now suppose that these imaginary animals, while remaining without thickness, have the form of a spherical, and not of a plane figure, and are all on the same sphere, from which they cannot escape. What kind of a geometry will they construct? It is clear that they will attribute to space only 2 dimensions. The straight line to them will be the shortest distance from one point on the sphere to another, that is to say, an arc of a great circle. In a word, their geometry will be spherical geometry. What they will call space will be the sphere on which they are confined, and on which take place all the phenomena with which they are acquainted. Their space will therefore be unbounded, since on a sphere one may always walk forward without ever being brought to a stop, and yet it will be finite, the end will never be found, but the complete tour can be made. Well, Riemann's geometry is spherical geometry extended to 3 dimensions. To construct it, the German mathematician had, first of all, to throw overboard not only Euclid's postulate, but also the first axiom that only one line can pass through 2 points. On a sphere, through 2 given points, we can, in general, draw only one great circle, which, as we have just seen, would be to our imaginary beings a straight line. But there was one exception. If the 2 given points are at the ends of a diameter, an infinite number of great circles can be drawn through them. In the same way, in Riemann's geometry, at least in one of its forms, through 2 points only one straight line can in general be drawn, but there are exceptional cases in which through 2 points an infinite number of straight lines can be drawn. So there is a kind of opposition between the geometries of Riemann and Lobachevsky. For instance, the sum of the angles of a triangle is equal to 2 right angles in Euclid's geometry, less than 2 right angles in that of Lobachevsky, and greater than 2 right angles in that of Riemann. The number of parallel lines that can be drawn through a given point to a given line is 1 in Euclid's geometry, none in Riemann's, and an infinite number in the geometry of Lobachevsky. Let us add that Riemann's space is finite, although unbounded in the sense which we have above attached to these words. Spaces with constant curvature. One objection, however, remains possible. There is no contradiction between the theorems of Lobachevsky and Riemann, but however numerous are the other consequences that these geometers have deduced from their hypotheses, they had to arrest their course before they exhausted them all, for the number would be infinite. And who can say that if they had carried their deductions further, they would not have eventually reached some contradiction? This difficulty does not exist for Riemann's geometry, provided it is limited to 2 dimensions. As we have seen, the 2-dimensional geometry of Riemann, in fact, does not differ from spherical geometry, which is only a branch of ordinary geometry, and is therefore outside all contradiction. Beltrami, by showing that Lobachevsky's 2-dimensional geometry was only a branch of ordinary geometry, has equally refuted the objection as far as it is concerned. This is the course of his argument. Let us consider any figure whatever on a surface. Imagine this figure to be traced on a flexible and inextensible canvas, applied to the surface in such a way that when the canvas is displaced and deformed, the different lines of the figure change their form without changing their length. As a rule, this flexible and inextensible figure cannot be displaced without leaving the surface. but there are certain surfaces for which such a movement would be possible. If we resume the comparison that we made just now, and imagine beings without thickness living on one of these surfaces, they will regard as possible the motion of a figure all the lines of which remain of a constant length. Such a movement would appear absurd, on the other hand, to animals without thickness living on a surface of variable curvature. These surfaces of constant curvature are of two kinds. The curvature of some is positive, and they may be deformed so as to be applied to a sphere. The geometry of these surfaces is therefore reduced to spherical geometry, namely Riemann's. The curvature of others is negative. Beltrami has shown that the geometry of these surfaces is identical with that of Lobachevsky. Thus, the two-dimensional geometries of Riemann and Lobachevsky are connected with Euclidean geometry. Interpretation of non-Euclidean geometries. Thus vanishes the objection so far as two-dimensional geometries are concerned. It would be easy to extend Beltrami's reasoning to three-dimensional geometries, and minds which do not recoil before space of 4 dimensions will see no difficulty in it, but such minds are few in number. I prefer then to proceed otherwise. Let us consider a certain plane, which I shall call the fundamental plane, and let us construct a kind of dictionary, by making a double series of terms written in 2 columns, and corresponding each to each, just as in ordinary dictionaries the words in 2 languages which have the same signification correspond to one another. Space, the portion of space situated above the fundamental plane. Plane, sphere cutting orthogonally the fundamental plane. Line, circle cutting orthogonally the fundamental plane. Sphere, sphere, circle, circle, angle, angle, distance between 2 points, logarithm of the anharmonic ratio of these 2 points and of the intersection of the fundamental plane with the circle passing through these 2 points and cutting it orthogonally, etc. Let us now take Lobachevsky's theorems and translate them by the aid of this dictionary, as we would translate a German text with the aid of a German-French dictionary. We shall then obtain the theorems of ordinary geometry. For instance, Lobachevsky's theorem: the sum of the angles of a triangle is less than 2 right angles, may be translated thus: if a curvilinear triangle has for its sides arcs of circles which, if produced, would cut orthogonally the fundamental plane, the sum of the angles of this curvilinear triangle will be less than 2 right angles. Thus, however far the consequences of Lobachevsky's hypotheses are carried, they will never lead to a contradiction. In fact, if 2 of Lobachevsky's theorems were contradictory, the translations of these 2 theorems made by the aid of our dictionary would be contradictory also. But these translations are theorems of ordinary geometry, and no one doubts that ordinary geometry is exempt from contradiction. Whence is the certainty derived, and how far is it justified? That is a question upon which I cannot enter here, but it is a very interesting question, and I think not insoluble. Nothing, therefore, is left of the objection I formulated above. But this is not all. Lobachevsky's geometry, being susceptible of a concrete interpretation, ceases to be a useless logical exercise, and may be applied. I have no time here to deal with these applications, nor with what Herr Klein and myself have done by using them in the integration of linear equations. Further, this interpretation is not unique, and several dictionaries may be constructed analogous to that above, which will enable us, by a simple translation, to convert Lobachevsky's theorems into the theorems of ordinary geometry. Implicit axioms. Are the axioms implicitly enunciated in our textbooks the only foundation of geometry? We may be assured of the contrary when we see that, when they are abandoned one after another, there are still left standing some propositions which are common to the geometries of Euclid, Lobachevsky, and Riemann. These propositions must be based on premises that geometers admit without enunciation. It is interesting to try and extract them from the classical proofs. John Stuart Mill asserted that every definition contains an axiom, because by defining we implicitly affirm the existence of the object defined. That is going rather too far. It is but rarely in mathematics that a definition is given without following it up by the proof of the existence of the object defined, and when this is not done, it is generally because the reader can easily supply it. And it must not be forgotten that the word existence has not the same meaning when it refers to a mathematical entity as when it refers to a material object. A mathematical entity exists provided there is no contradiction implied in its definition, either in itself or with the propositions previously admitted. But if the observation of John Stuart Mill cannot be applied to all definitions, it is none the less true for some of them. A plane is sometimes defined in the following manner. The plane is a surface such that the line which joins any two points upon it lies wholly on that surface. Now, there is obviously a new axiom concealed in this definition. It is true we might change it, and that would be preferable, but then we should have to enunciate the axiom explicitly. Other definitions may give rise to no less important reflections, such as, for example, that of the equality of two figures. Two figures are equal when they can be superposed. To superpose them, one of them must be displaced until it coincides with the other. But how must it be displaced? If we ask that question, no doubt we should be told that it ought to be done without deforming it, and as an invariable solid is displaced. The vicious circle would then be evident. As a matter of fact, this definition defines nothing. It has no meaning to a being living in a world in which there are only fluids. If it seems clear to us, it is because we are accustomed to the properties of natural solids, which do not much differ from those of the ideal solids, all of whose dimensions are invariable. However, imperfect as it may be, this definition implies an axiom. The possibility of the motion of an invariable figure is not a self-evident truth. At least, it is only so in the application to Euclid's postulate, and not as an analytical a priori intuition would be. Moreover, when we study the definitions and the proofs of geometry, we see that we are compelled to admit without proof not only the possibility of this motion, but also some of its properties. This first arises in the definition of the straight line. Many defective definitions have been given, but the true one is that which is understood in all the proofs in which the straight line intervenes. It may happen that the motion of an invariable figure may be such that all the points of a line belonging to the figure are motionless, while all the points situated outside that line are in motion. Such a line would be called a straight line. We have deliberately, in this enunciation, separated the definition from the axiom which it implies. Many proofs, such as those of the cases of the equality of triangles, of the possibility of drawing a perpendicular from a point to a straight line, assume propositions the enunciations of which are dispensed with, for they necessarily imply that it is possible to move a figure in space in a certain way. The fourth geometry. Among these explicit axioms, there is one which seems to me to deserve some attention, because when we abandon it, we can construct a fourth geometry, as coherent as those of Euclid, Lobachevsky, and Riemann. To prove that we can always draw a perpendicular at a point A to a straight line AB, we consider a straight line AC movable about the point A, and initially identical with the fixed straight line AB. We then can make it turn about the point A until it lies in AB produced. Thus we assume two propositions. First, that such a rotation is possible, and then that it may continue until the two lines lie the one in the other produced. If the first point is conceded and the second rejected, we are led to a series of theorems even stranger than those of Lobachevsky and Riemann, but equally free from contradiction. I shall give only one of these theorems, and I shall not choose the least remarkable of them. A real straight line may be perpendicular to itself. Lee's theorem. The number of axioms implicitly introduced into classical proofs is greater than necessary, and it would be interesting to reduce them to a minimum. It may be asked, in the first place, if this reduction is possible, if the number of necessary axioms and that of imaginable geometries is not infinite. A theorem due to sophist Lee is of weighty importance in this discussion. It may be enunciated in the following manner. Suppose the following premises are admitted. 1. Space has n dimensions. 2. The movement of an invariable figure is possible. 3. P conditions are necessary to determine the position of this figure in space. The number of geometries compatible with these premises will be limited. I may even add that if n is given, a superior limit can be assigned to P. If, therefore, the possibility of the movement is granted, we can only invent a finite and even a rather restricted number of three-dimensional geometries. Riemann's geometries. However, this result seems contradicted by Riemann, for that scientist constructs an infinite number of geometries, and that to which his name is usually attached is only a particular case of them. All depends, he says, on the manner in which the length of a curve is defined. Now, there is an infinite number of ways of defining this length, and each of them may be the starting point of a new geometry. That is perfectly true, but most of these definitions are incompatible with the movement of a variable figure such as we assume to be possible in Lee's theorem. These geometries of Riemann, so interesting on various grounds, can never be, therefore, purely analytical, and would not lend themselves to proofs analogous to those of Euclid. On the nature of axioms. Most mathematicians regard Lobachevsky's geometry as a mere logical curiosity. Some of them have, however, gone further. If several geometries are possible, they say, is it certain that our geometry is the one that is true? Experiment no doubt teaches us that the sum of the angles of a triangle is equal to 2 right angles, but this is because the triangles we deal with are too small. According to Lobachevsky, the difference is proportional to the area of the triangle, and will not this become sensible when we operate on much larger triangles, and when our measurements become more accurate? Euclid's geometry would thus be a provisory geometry. Now, to discuss this view, we must first of all ask ourselves, what is the nature of geometrical axioms? Are they synthetic a priori intuitions, as Kant affirmed? They would then be imposed upon us with such a force that we could not conceive of the contrary proposition, nor could we build upon it a theoretical edifice. There would be no non-Euclidean geometry. To convince ourselves of this, let us take a true synthetic a priori intuition, the following, for instance, which played an important part in the first chapter. If a theorem is true for the number 1, and if it has been proved that it is true of n plus 1, provided it is true of n, it will be true for all positive integers. Let us next try to get rid of this, and while rejecting this proposition, let us construct a false arithmetic analogous to non-Euclidean geometry. We shall not be able to do it. We shall be even tempted at the outset to look upon these intuitions as analytical. Besides, to take up again our fiction of animals without thickness, we can scarcely admit that these beings, if their minds are like ours, would adopt the Euclidean geometry, which would be contradicted by all their experience. Ought we, then, to conclude that the axioms of geometry are experimental truths? But we do not make experiments on ideal lines or ideal circles, we can only make them on material objects. On what, therefore, would experiments serving as a foundation for geometry be based? The answer is easy. We have seen above that we constantly reason as if the geometrical figures behaved like solids. What geometry would borrow from experiment would be, therefore, the properties of these bodies. The properties of light and its propagation in a straight line have also given rise to some of the propositions of geometry, and in particular to those of projective geometry, so that from that point of view one would be tempted to say that metrical geometry is the study of solids, and projective geometry that of light. But a difficulty remains, and is unsurmountable. If geometry were an experimental science, it would not be an exact science. It would be subjected to continual revision. Nay, it would from that day forth be proved to be erroneous, for we know that no rigorously invariable solid exists. The geometrical axioms are therefore neither synthetic a priori intuitions nor experimental facts. They are conventions. Our choice among all possible conventions is guided by experimental facts, but it remains free, and is only limited by the necessity of avoiding every contradiction. And thus it is that postulates may remain rigorously true even when the experimental laws which have determined their adoption are only approximate. In other words, the axioms of geometry, I do not speak of those of arithmetic, are only definitions in disguise. What then are we to think of the question, is Euclidean geometry true? It has no meaning. We might as well ask if the metric system is true, and if the old weights and measures are false, if Cartesian coordinates are true and polar coordinates false. One geometry cannot be more true than another, it can only be more convenient. Now Euclidean geometry is, and will remain, the most convenient. First, because it is the simplest, and it is not so only because of our mental habits, or because of the kind of direct intuition that we have of Euclidean space. It is the simplest in itself, just as a polynomial of the first degree is simpler than a polynomial of the second degree. Secondly, because it sufficiently agrees with the properties of natural solids, those bodies which we can compare and measure by means of our senses. End of chapter 3.